Today, we're diving into a process that makes everything from the gears in your car to parts in a jet engine possible. It's called carburizing. It's a century-old art of hardening steel. But now, that old-school art is getting a serious high-tech upgrade with something called a smart furnace. So, let's fire it up.
So, right off the bat, here's the big challenge. Picture a gear in a car's transmission. The surface needs to be incredibly hard to survive all that friction. And this is a big but, if you make the whole gear that hard, it becomes brittle. Like glass. One good shock and it could literally shatter. So the real puzzle is, how do you give one single piece of steel this kind of dual personality? And for over 100 years, the answer has been carburizing. The idea is actually pretty elegant. You basically cook the steel parts in a super carbon-rich environment. At high temperatures, carbon atoms literally soak into the surface, creating this thin, high-carbon case. Meanwhile, the inside, the core, stays low carbon, which means it stays tough and flexible. You get the best of both worlds, a wear-proof outside with a shock-resistant inside. Now, for most of history, getting this right was way more art than science. It was all about experience, gut feelings, and secret family recipes passed down through generations. But today, we have the smart furnace. And this isn't just a hotter oven, it's a genuine high-tech marvel. The promise here is to finally take all the guesswork out of the equation and shoot for absolute metallurgical perfection with every single batch. So, what really makes a furnace smart? Well, it's this incredible continuous feedback loop. You've got analyzers constantly tasting the atmosphere inside. You have AI algorithms crunching that data in real time, making tiny adjustments. You've got sensors buried deep inside, feeding back live info, and all of it is being crunched by models that are calculating exactly how fast carbon is diffusing into the steel. The whole system is optimizing itself on the fly. Which, of course, leads to the big question. With this insane level of control, have we finally beaten all the old headaches that come with heat treatment? Can you just, plug in the perfect recipe, press a button, and get a flawless part every single time? Well, as you might guess, the reality is a little more complicated than that. Let's start with our first reality check, distortion. This is a massive problem. The intense heat and super fast cooling can cause these perfectly machined parts to warp, twist, and bend. And if they're not the exact right shape, they're basically useless, expensive paperweights. To really get why things warp, you have to look at the most violent part of the process, the quench. This is where you flash cool the red-hot steel to lock in that hard surface. The old-school way, you'd plunge it into a giant vat of oil. It's chaotic. The oil boils instantly, creating these vapor bubbles that make the cooling totally uneven. But modern vacuum furnaces allow for a much more graceful method, high-pressure gas quenching. Instead of a violent splash, the part is bathed in a perfectly controlled, uniform flow of gas. It cools things down much more gently and evenly. And the results? They're not just a little better, they're dramatic. This chart shows the runout, basically the wobble in gears after they've been treated. With the old oil quench, you can see the distortion is all over the map. It's a huge, unpredictable mess. Now, look at the gas quench. Not only is the average distortion cut way down, but look how tight that grouping is. The results are incredibly consistent. And that predictability, that's everything. And this brings us to a really crucial insight. The single biggest leap forward in fighting distortion didn't actually come from the smart sensors controlling the heating part. It came from a fundamental change in the cooling part, the move from a chaotic liquid splash to a controlled gas quench. It's the vacuum furnace technology itself that enables this huge improvement. Okay, reality check number 2. Let's go deeper. We're going to move past the physical shape of the part and look at its very atomic structure, its microstructure, to see what's happening with these invisible villains on the inside. And first, let's be clear, this is a huge, undeniable win for smart furnaces. Because they can operate in a pure vacuum with no oxygen, they completely wipe out a nasty defect called intergranular oxidation. Think of it as a kind of microscopic rust that forms between the steel's crystals in old-school furnaces, making the surface weaker. With smart tech, that problem is just gone, solved. But as we said, solving one problem doesn't mean you've solved them all. There is another, much more stubborn metallurgical villain that even the smartest furnace in the world has to fight. And that villain's name is retained austenite. So here's what's supposed to happen. When the steel is hot, its atoms are arranged in a structure called austenite. The whole point of the quench is to shock all of it into transforming into a new, super hard structure called martensite. But sometimes, some of that austenite just doesn't transform. It kind of
didn't get the memo. It gets left behind, soft and unstable, trapped inside the new hard structure. And having this leftover stuff hanging around is a really big deal. It makes the surface softer, less wear-resistant. It can reduce the part's fatigue life. And because it's unstable, it can slowly transform later on, causing the part to actually change its shape and size long after it's been put into service. It completely undermines the whole point of the treatment. Okay, so this is where the smarts of the furnace really come back into play. It can't just magically wish retained austenite away, but it can manage it with incredible finesse. By running these super complex, multi-step recipes, like something called stage carburizing, the furnace can carefully trick the steel into behaving, slashing the amount of retained austenite by a whopping 45%. This is a level of intricate control that is just flat out impossible in a traditional furnace. So let's bring this all together. What is the true advantage of a smart furnace? If it's not actually inventing some brand new kind of metallurgy, what is it that makes it so special? Well, the real power boils down to two things. First, it enables complexity. The second-by-second control allows engineers to design and, more importantly, reliably run these incredibly advanced treatment plans that used to just be theoretical. Second, and this is maybe the biggest deal, it ensures consistency. Those feedback loops and AI adjustments mean the furnace hits the perfect target every time, automatically compensating for all the little real-world things that would throw an older process completely off course. And that right there is the bottom line. Smart furnace tech isn't about creating some new magic super steel. Its revolutionary power is taking what metallurgists already know is the perfect result and then delivering that result with near perfect precision and repeatability every single time. It is the ultimate tool for control. Which means the human expert, the metallurgist, is actually more critical than ever. Their job is just changed. They're not furnace operators anymore, trying to wrestle a finicky machine into submission. They're now more like architects, designing these incredibly sophisticated recipes for a precise and powerful instrument, pushing the absolute limits of what we can reliably create. And that leaves us with one final, fascinating thought. For 100 years, the fight was against the random, unpredictable nature of heat. But now that we are achieving near-perfect control, the question isn't, can we make the part correctly anymore? The question is, what new, incredible things can we design knowing the steel will be perfect every single time? The possibilities are really just starting to open up.